Hello, Mom, over here. I'm sure that you have heard of NASA before, the National Aeronautics Space Agency of the United States, and you have somehow marveled, wondered, and felt amazement whenever you hear news about breakthroughs, images that NASA uploads, projects that they have launched recently. And not only NASA, of course, we have to acknowledge as well the efforts of the other space agencies like our own DOST, Pag-asa efforts to launch the satellite, Diwata, and the other similar satellites made by our Filipino scientists. There also is the efforts of the Indian Space Agency to launch a probe to the moon in order to explore the South Pole. So there are several efforts as a collective that humanity has been trying to explore the outer space for a very long time. And it gives us a sense of mystery and wonder to know that we are living in a very in a time where there are so many breakthroughs that allows us to explore outer space. Now, these concepts, the sciences that allows our engineers, our cosmonauts, and astronauts to explore outer space, of course, anchors on the field of astronomy. Now, for today's video, we will be exploring the concept of astronomy, not yet modern astronomy, but the foundational astronomy. Of course, we will not be able to fully appreciate the breakthroughs of our modern scientists without looking at the efforts of classical astronomy and the historical development of astronomy. So for today, our learning objectives is first to explain how the Greeks knew that the Earth is spherical. Second, cite examples of astronomical phenomena known to astronomers before the advent of telescopes. And the third, explain how Brahe's innovations and extensive collection of data and observational astronomy paved the way for Kepler's discovery of his laws for planetary motion. Now, in the recent decade, there has been a resurgence of, sadly, the flat Earth theory. Now, the flat Earth theory stubbornly states that the Earth is not spherical, but instead flat, that the Earth is flat, and there are multiple conspiracies surrounding why the Earth exactly is flat. Now, probably because there has been some rising distrust towards science and government authorities, which led to the resurgence of conspiracy theories. But actually, this theory, this hypothesis, this misconception has been debunked for hundreds, thousands of years, even by our early predecessors. How back in history have we rejected this theory? Well, the Greeks has already rejected his theory. Even the Greeks knew that the Earth is not flat, given that they have made some misconceptions along the way. But it has been apparent to our philosophers, our Greek thinkers, that the Earth was not flat. For example, Aristotle was recorded to observe the stars and observe that whenever um, the night progresses, the stars does not even stay in the same place. Because if you can imagine, if the Earth is flat, therefore the image of the stars must be constant as well, because the Earth is completely stagnant. So it doesn't make sense that the Earth, if it's stagnant, the stars would also be stagnant as well. But according to Aristotle, he had observed that depending on the time of the night, the stars may shift from one position to another. Furthermore, depending on the time of the year, the stars are not even the same. So there's a missing thoughts or missing explanation why our heavens are constantly changing. Now, the first person to make an experiment which supports the idea that the Earth is not flat is Aristophanes of Cyrene. Now, the location of these experiments are very important. Now, Aristophanes of Cyrene had an observation during the summer solstice. The summer solstice is a particular time in our Earth's yearly calendar wherein the sun is closest to the Earth. Therefore, the sun would shine the brightest based on our perspective, and it will also shine longer, the longest time in a day. So usually it can last for 12 or more hours because of the sun's nearness or approximation to the Earth. Now, in order to see if the Earth is indeed flat, Aristophanes of Cyrene used the shadows and, of course, some trigonometry. Quick side fact, trigonometry is a well-used mathematics when we are measuring large distances. Of course, you cannot manually measure the distance of the sun and the stars and the moon. Instead, they just use the distance of the Earth. They use trigonometry in order to um, deduce order to calculate the distances of stars, the galaxies, and so on, based on how fast light travels, angles, and of course the size of our planet, which is quite amazing. Now, the Greeks have started to use this concept as well. So let me go ahead and discuss what did Aristophanes do. So in his first observation, he noticed that Cyrene, which is very close to the equator, does not have a shadow at exactly 12 o'clock during the summer solstice. So here, because the sun is directly shining above Cyrene because it's close to the equator, it does not cast a shadow at exactly 12 noon. But he have heard that this is not the case in other locations. Therefore, he traveled further to the borders of the Greek territory and went to Alexandria. Now he put a stick in the ground and measured the angle of the shadow during the summer solstice. And he noticed that there is an angle that instead of having no shadow at all or a direct shadow above, there is a 7-degree difference. Now, take a look of the difference. Now, let's say that the earth is flat. Okay? If the earth is flat, then there should be no angle because the exposure or the position of the stick would be directly pointing at the sun. Therefore, the sun will shine on them the same way, creating no shadows at all during the summer solstice at noon. However, since the earth is actually curved, the stick at Alexandria is also curved, therefore creating a 7-degree shadow. By that simple, elegant experiment alone, he was able to prove that the Earth actually have a curvature and is not flat. Now, just to summarize the idea by Aristophanes, let's just read this paragraph. If the sun's rays are coming in at the same angle at the same time of day, so saying that the earth is flat, and a stick in Alexandria is casting a shadow while a stick in Cyrene is not, it must mean that the earth's surface is curved. Now, this experiment is somewhat crude because you had to manually calculate and measure everything, but it's a simple experiment that already proves that the earth is actually curved. Now, um, we as a people, as a human beings, we have been observing the night sky for a very long time. And Aristophanes wouldn't be able to tell that difference without the previous observations of the civilizations before him. Now, as I've mentioned, we have been well fascinated with the heavens for a very long time. And even before the advent of telescopes or discovery of telescopes, we have recorded observations of the night sky. We have added it incorporated it into various cultures. So for example, in our first picture here, the gnomon or the sundial is a Babylonian and Egyptian tool in order to tell the time of day and also predict uh, the changes in the year. So we have already observed that there is a constant um, pattern in the changes of the day, the night, and so on. Now, the Egyptians also have recorded the constellations or what stars are present depending on the time of the month. So they have depended on the constellations to tell, is it time to harvest? Is it time to plant? We have also recorded the stages or the phases of the moon, and we have incorporated it even in our modern calendars. Now, certain cultures even put high importance into the phases of the moon, like the Islam and the Chinese, which they have superstitions and belief around the phases of the moon. We have also predictions of when the lunar and the solar eclipse will occur, and we have made stories about them. So, for example, the Vikings thought that whenever a solar eclipse occurs, a dragon is actually eating the sun, but in reality, it's just the moon hiding or hiding or eclipsing the sun. That's why we cannot see the sun at a certain point or a certain short period of time. And according to the Vikings, you have to scare away the dragon that have swallowed the sun whole, and they made lots of noise just to scare the dragon away. But it's just the moon moving through its phases, and it will normally go back as it were. So we have interesting stories like that, and also we have made architectures just to observe the motion of the planets, like the Mayan who have made platforms in order to observe Venus better. So astronomy has been deeply incorporated in our culture, and of course we as a humanity will try to look into heavens more. We will keep on developing more sophisticated tools in order to observe the heavens, like the telescope. And with the discovery of the telescope, of course, we have also questioned like what is the correct his model to show the planetary motion. Now, since we have been observing the heavens for a long time, we were able to say that we are not alone. By we are not alone, I mean we are not the only planet in our solar system. For a very long time, even the Mayans have observed the presence of Venus and also the Greeks. So, how do we show or how do we understand the motion of the heavens? Now, there are two prevailing thoughts under this concept. The first one is the Greek geocentric model. So as the term suggests, geo, which means earth, and centric. So the earth is in the center of the solar system, and this thought has come first, at least recorded, during the time of the Greeks. Now, if you remember your Greek mythology, the earth is at the center of the solar system because the earth is surrounded by the heavens where the gods live, and the gods observe their creation surrounding. So yes, we are as the earth is surrounded by the heavens, and they are constantly observing us. So by that concept, that is indeed geocentric. Now they of course observed that there is a presence of the sun, the moon, the other planets. So how do we put that into the picture? Now by their understanding, the heavens are perfect. So everything that is heavenly must be perfect as well. So the sun, the moon, the stars, all of them are perfect spheres, and all of them move around our planet in perfect spheres or in perfect circles because the gods are perfect. Now, that concept has been proposed earliest by Plato, which was passed down to his students, namely Eudoxus and Aristotle. But it was Ptolemy who was able to make a very defined, sophisticated geocentric model with the detailed observation of the moon, the sun, and the stars, and so on. So, technically, he was right at some cases of how the moon um, revolves around the earth. It was accurate enough for us, for at least for human beings, to try to understand um, how the heavens behave for at least 1,500 years. There are, of course, philosophers who went against this model. So here comes the heliocentric model, or helio meaning the sun and center. So Aristarchus of Samos, also dubbed as the Greek Copernican, is the first ever person recorded to have proposed the heliocentric model. So he presented that the center of our solar system or our universe is actually at the sun, and we, the earth, is simply revolving around it while the moon is revolving around us. So you can see here in his drawings, these are from Aristarchus' work, that this is the sun, the moon revolves around us. Sorry, this is the earth. Then the earth revolves around the sun, and the moon revolves around the earth. So he has some idea of how our solar system behaves. However, he did not gain much support from his peers because, well, who is Aristarchus? Really, the more famous philosophers were Plato, Aristotle. So if Plato and Aristotle says that the solar system is geocentric, then the Greeks most likely believe them more than Aristarchus. But of course, the truth will always prevail, and it was Nicholas Copernicus who brought back the heliocentric model. Now, this was during the heavy influence of um, the Catholic religion. So during the early days of Catholicism, they absorb or they have accepted the geocentric model. The Earth is at the center of the universe because we are God's creation. But Nicholas Copernicus came with the sun-centered model, also known as the Copernican model. So far he is right that the sun is the center of the solar system and the earth simply revolves, which is actually against the church teaching, which is a big deal back then. But unfortunately his model was not yet accurate because he did not change the orbit of the planets. It was enough to create certain predictions on where the other um, celestial bodies would be following the circular orbits. It still wasn't quite right, and it did not predict um, the motion of the heavenly bodies to a dot. So there is some changes still needed to be done. Now, the additional changes came through the contributions of two other notable astronomers. Now, back then, the only astronomers are the rich people. So Tycho Brahe was definitely rich. He was from Sweden, and he has an observation facilities. He has a tower where he has a telescope wherein he can observe the motion of solar system or of the heavenly bodies. Now Tycho Brahe observed the orbit of Mars and the other heavenly bodies, and he recorded them religiously. But he was an avid supporter of the geocentric model. He was using his observations to prove that the geocentric model is correct. However, even before his death, he could not make it work. He hired his assistant named Johann Kepler in order to help him make sense of all his observations. However, Tycho Brahe did not fully trust Johann Kepler because Johann Kepler is an advocate of the heliocentric model. So they are at a bit of misunderstanding. Now, Tycho Brahe eventually died, and Johann Kepler got the copy of all his observations. And that's when everything clicked for Johann Kepler because he eventually realized that the Copernican model is indeed correct with some modifications. Now, according to Kepler, he noticed that the orbit that the previous astronomers was trying to use was perfect circular orbits, but that does not make sense because that's not what the planets are actually doing. Instead, they are using an elliptical orbit, or they are going through an elliptical orbit whenever they uh, orbit or revolve around the the sun. And that's when the laws of planetary motion was created. So with the complete observations of Tycho Brahe, Johann Kepler was able to make the three laws of planetary motion. So here, let me discuss the three laws of planetary motion. The first one, the Kepler's first law, the orbit of each planet around the sun is an ellipse or an elliptical orbit with the sun at one focus. Now take note, the sun is not at the center. Okay, the sun is not at the center of this elliptical orbit. There is some uh, misalignment, like it's not at the center. There is a particular position in our orbit wherein we are at the closest at the sun's position. That's called the perihelion. So the distance between the sun and the orbit where we are closest is the perihelion, and on the other side we have the aphelion. And then this dark blue or solid blue line is um, where the Earth follows its orbit. Now imagine the sun, because the sun has force, it has gravity. Now as the sun is pulling the Earth, it will, so let me draw this, it will pull the Earth to its orbit, okay? And then it will accelerate as it moves towards the sun, but it's already moving it to its orbit, so it will not crash. Instead, it will accelerate and it will curve, and then it will move farther to space. Now, as it's moving away from the sun, its motion will go a bit slower until it is affected and pulled back by gravity again, and it will accelerate and then curve again and then be propelled back into outer space again. That's usually or that is the motion of our Earth and also the other planets in our solar system. So each of our planets have a perihelion and aphelion relationship with our sun. So the perihelion is often associated during the summertime where it's hottest, and aphelion during the winter time wherein we are farthest away from the sun. So pretty much this already explains why certain seasons exist. So at the aphelion, we are very farther from the sun, therefore it's very hot. Very cold. And then during the perihelion, we are closest to the sun, therefore the summertime occurs, so it's very hot. Okay, so that's the Kepler's first law. Now, the Kepler's second law states that as a planet moves around its orbit, it sweeps out equal areas in equal times. Basically, it just states that the planet maintains a particular speed, okay, or a particular speed and orbit. Every year, annually, uh, there is a same pattern, like it maintains its constant movement. So for example, Pluto is no longer considered as a planet because it does not follow Kepler's second law. It does not maintain its orbit, and it does not complete its orbit at the same instances, which, for example, the Earth, we follow the same amount of time. So we can rely on the 365.25 days, we will be able to complete the orbit. But that's not the case for Pluto. It's quite unpredictable. So we can estimate when Pluto will finish its orbit, but it's not constant. So let's read further the description here of our image. So near the perihelion, in any particular amount of time, such as 30 days, a planet sweeps out an area that is short but wide. So that means there is a particular period wherein the planet will accomplish the perihelion. And then on the other side, near the aphelion, in the same amount of time, a planet sweeps out an area that is long but narrow. So it simply states here that there is a, like in an equal area, amount of area. So this area, for example, here, and the area around here is pretty much the same because we are measuring the area of space. So since the planet follows a certain orbit, it follows a certain speed. So regardless of the acceleration, in relation to the sun, it will still occupy the same amount of area at the same amount of speed. That's the Kepler's second law. Now, for the Kepler's third law, this is mostly relating to the ratio of how fast the planets will finish its orbit. This is called the law of harmonies because the planets follows a certain ratio wherein p squared is equal to a cubed. So the p is the orbital period in years and a is the average distance from the sun in AU. If we simply explain it, this means that the sun at the center and then the planets, okay, all of the planets orbit the sun. That's established. Now, the farther the planet is from the sun, the more time it needs in order to accomplish the orbit. So, of course, we all know that that is because of gravity. The less gravity there is, the most likely the planet will move um, a bit slower because there is less gravity pulling the planet back to the sun and then move to its orbit. Now, at the time, Kepler did not know that, but he observed that it's the same for all the planets. The closer, for example, Mercury is closest to the sun, therefore it finishes its orbit faster. Venus is a bit farther from the sun, but it still finishes its orbit at the same period, but not as fast as Mercury. Followed by Earth, we are farther. We finish our orbit at the same time every year, but not as fast as Mercury, Venus, and so on. So the planets follows this ratio. The period in years is always in ratio with the average distance of the planet of the sun in astronomical units. So there we go. That's the three laws of planetary motion. Now, of course, to be considered as a planet, they must all follow the three laws. Now, if you are interested in reading furthermore, these are some references that might interest you. I will also link the physics classroom reference in our BBL just in case you want an extra reading. If you have any questions about the concepts I have discussed in this video, don't be shy and send me a message. That's all for me today. Bye!